Okay, I think we can start. Can you hear? Can you see the slides?
Yeah.
Okay, that's great. So welcome everyone to the last lesson of this course. As you probably know, this is the lesson number 3 and also the conclusion of this course. So what are we going to do today is to further explore the topic of integer programming by looking at a specific case of integer programming that is called binary programming. That is the case where the integer variables can only assume values 0 or 1. But before that, I want to quickly go through the solution of the homework, and so we can see how to solve it, even though those of you who submitted the homework did a pretty good job. So before starting with the solution of the homework, one communication is this. I, at the beginning, was thinking about splitting people into groups and then giving points according to the result of the homework. But because I've not received enough submissions to justify that, what will happen is that at the end, when you submit also the homework number 2, I will just sum up the points for everyone. There will be a ranking. And then according to the ranking for the first, I have to see maybe 6, 8 positions, I don't know, there will be some prizes, maybe some vouchers, something like that. We are still discussing with the management. So the idea of the groups, unfortunately, is not feasible because there may be the situation where maybe just one person submitted the homework and the other didn't. So it's not fair to give a reward to everyone. So this was the question, right? This couple of equations, and then we had 3 questions. So let's see what we can do to solve that. First thing is we need to assign variables to each symbol. Here I put A, B, C, D, E. Of course, there were also some other options. Some of you during the homework, they used the sets. So for example, the index 1, 2, 3, 4, 5, and then they call the variable X. So something like, instead of having these, you can have a set with the elements 1 to 5, right? S is this set, and then you have X of S. So you can save space in a way. That is good because it's basically using what we learned last time. When you have these, of course, each symbol is an integer variable between 0 and 9. And we know that we have an order because the first one we see is the largest and so on. So because we cannot have strict inequality, we can do something like that. We can use a non-strict inequality, and then we can use a +1 or plus 0 point something, whatever. The point is that we are exploiting here the fact that the variables are integer. Okay, so of course, this would have been different if they were continuous because this number is what, but if they are integer, then we can avoid the issue of not being able to write strict inequality by having this kind of formulation here. Wait a second, someone got the mic. Can you mute yourself? Whoever is. Okay, wait a second. Okay. So question number 1 was finding the solution that minimize the value associated with the pentagon, so it's symbol D in my formulation, and you can see here the mod file. So what we do, we define the 5 variables, integer 0 to 9. We want to minimize D, that is the symbol we are interested in, and the 2 equations that were represented by the symbols can be written like that. Remember, if you have something like that, this is 10 times this plus this, okay? So someone asked me about this because there was some confusion. This is not a multiplication. So this thing here is not this times this, okay? If you have a situation like that, where you have a product between integer variables and Or maybe if you have a product even between variables and no more than one is continuous, there are some techniques to transform it into a linear operator. So if you found these problems in your research, you can let me know. I can share with you how you can linearize this kind of nonlinear expressions. Anyway, we have these, so the two equations, and then we have the order constraints. And then when we solve this problem, of course, we have the round fight, and then we find the solution. Okay, so the objective is 1, and you see the symbol D is 1, and these are the 5 numbers. The second question, we wanted to minimize A. Okay, so basically we change the objective function, we run it again, and then we find that the minimum is 7. Some people may have found a different solution. Is fine. I mean, if the objective is the same, but this is different, it doesn't mean it's wrong. It just means that there are different solutions, and then simplex, because I'm using a different version. I think you guys are using version 20. I have this one. So because of different default setting, other solutions can be found, but it doesn't mean that if this one is not the same, is wrong. If the objective function is the same, then it's fine. And finally, we wanted to minimize the sum of the values of the symbols, basically summing A, B, C, D, E. But there was this, the pentagon is an even number. So I've seen different solutions to represent this condition. Some people use the by. There is a command called by where you can define a variable in steps. So for example, you say, hey, it can be only 0, 2, 4, 6, 8. Some people use this approach instead. That is basically, if I want that D is equal to 0, 2, 4, 6, 8 only, right? How can I do that? Well, I can say that D is 2 equal T, and T can be 0 to 4. So basically, for every value of T, if T is 0, 1, 2, 3, and 4, this is the corresponding value of T. So I am able to represent the condition I wanted. And then when you do that, and you solve the problem, you find that this is the solution. So the objective function is 20, you can see here, and this was the solution. And as you can see, D is an even number, is equal to 2. Okay? So this was the solution of the homework. Do you have any questions before we proceed? And also, I have a question for those of you who did not submit. I don't know if it's because you didn't have time or you did not understand how to solve it. If this is the case, if you had troubles in understanding, please let me know by email. If something was not clear, I can discuss with you, no problem. But if something is not clear, really don't feel free to write to me to ask for explanation. Okay, because the important thing for me is that you understand the concept, the topic, and that you know, if the homework was hard for some reason, feel free to share with me, and then I will do my best to clarify what was not clear. So, binary linear programming, that's the topic of today. And as usual, let's see how to state the problem. So as I say, this is a special case of MILP, where instead of having integer variables, we have binary, that means 0 or 1. So how to represent that? Well, it's the usual stuff, only that some of the variables now, they are 0 or 1. And why is this important? Because when you have integer variables, you can represent many things. But when you have 0, 1 variables, you can represent choices or logical conditions. That means, for example, if, then, and I will show you in the next slides what I mean. But basically, whenever you have to choose between doing or not doing something, then you can use binary variables. So for example, let's say you have two variables, and then you want to represent a condition, for example, the first one where only one among X and Y can be 1. And when you see 1, you can think about, for example, true, and 0 is false. This is one of the classical use of binary, right? So let's say you have two things and then you want that one among these two is true. Then how do you write it with the binary variables? You can use something like that. The sum is less than or equal to 1, right? So this way only one can be true, because if both were 1, then the sum will be 2. And sometimes when you have this variable, it's good to write the different cases. For example, you can write a table like that, right? And then you see, okay, what do I want to represent? Only one among X and Y can be 1. So these, and these are valid. This is not. So this constraint basically is making feasible only this case. Sorry, only these 3 cases. And this one is infeasible. Okay. So this is another way you can, because what is the point here? Since they are 0, 1, you can represent, if you have 3, 4, maybe maximum variables, all the different cases, all the different combinations, and then you can check if your constraint case by case is doing what it should do. So this one, X can be 1 only when Y is 1. We can write it like that, because if Y is equal to 0, then X is less than or equal to 0. That means X is equal to 0 because it's 0, 1. And when Y is 1, then X can be 0 or 1. Okay. Another one, X and Y are different. Well, you can write it like that. If X is 0, then Y is 1. If X is 1, then Y is 0. Another one could be this. If X is 0, then Y is 1. Okay. Why? Because if X is 0, Y is greater than or equal to 1. Actually, this one is wrong. Because if X is 1, no, this one is correct, actually, sorry. If X is 0, then Y is greater than or equal to 1. If X is 1, then Y is greater than or equal to 0, because the 1 goes on the right and then you have this. That means Y can be anything, because it's always 0 or 1. So greater than or equal to 0 is like not having this constraint. Now, there are many ways that you can combine these logical conditions to create situations like that. And I suggest you this paper that I uploaded on the website of the course. This one is a very nice paper where you have a list of a lot of conditions like that, especially you look at section 3. So I suggest you to have a look, especially for the last homework that I will present at the end of the lecture. Something inside here may be helpful. Okay, so it's uploaded on the website under material, I think, but you will find it. Okay, so this was the summary about binary linear programming. As you have seen, is basically the same as integer programming in terms of modeling. Really, the difference for us is that instead of using the keyword integer in our AMPL models, we will use the keyword binary. Or we can use the keyword integer and specify greater than or equal to 0 and less than or equal to 1. But what is very powerful about that is the flexibility that binary variables allow us to express in our models. For example, conditions like that. For example, yes, no, true, false kind of situations. Okay, is there any questions so far? No? Okay, so let's proceed. And as usual, now we have our session where we work together on a problem. And then after the break, I will give you the questions for you to work on. And then we move to the description of the last homework. Okay, so, oh, wait. We have a question, yeah?
So I just wanted to ask a simple question. I'm not sure if it's simple or not, but normally when we do any kind of analysis in general, right, in engineering, we do something known as sensitivity analysis, where we find out how the result changes when we have incremental changes in the parameters, for example. Is there any
Okay.
way to do such a thing for optimization? Because I'm a novice and I'm not sure. So, for
Sorry,
example,
what? Yeah,
is there
yeah.
any way to do sensitivity analysis in a more formal way other than just changing in the parameters and then looking at the output? So how would the optimal value change when we have an incremental change in that particular parameter or another parameter or a couple of parameters?
I mean, if you want, for linear programming, sensitivity analysis is a big topic. There are techniques to do that, but if you want to do it that way, is much more on the theoretical side. So I can share later with you if you want some material. When you are looking at linear programming, yes, there are some ways to look at, for example, how the cost, for example, of the objective function will change, will have an impact on the solution, how the parameters, and you can derive some formula that tells you more or less if you change by that much, you will get this kind of change. But is really, I would say, a lot has to deal with the theory behind the simplex algorithm, that is the algorithm that is used to solve the linear programming, maybe something about duality. So there is something, but is more on the theoretical side and is not something we have covered in this course. So if you are interested later, I can share something about that after the course. We have another, wait. Okay, Tanya, what do you mean by that? Oh, okay, then just right. I guess you're referring to, oh, I hope that with this exercise we do together, you will see how we can use binary. Okay, so just wait for this to be done, and then if after that is still not clear, you let me know. Okay. So today the problem is about golf. I don't know if you guys play golf. I did it, and it's not easy, but I guess this is not so hard, at least when we look at this application in optimization. The problem may be nonsense in practical terms, but we don't care. We just want to see how we can model problems and practice modeling, and in this case, binary linear programming modeling. So imagine, I hope you are familiar with the golf. You know, you are at the start, and then you have a hole that is, in this case, 330 meters away. And imagine that you are a really good player. So whenever you have a club, you know that you will hit that distance. So the hole is so far 330 meters, and then you have different clubs. So you have 3 clubs for the long distance, 3 for the medium, 3 for the short. Okay, and you can only use each club once. So for example, for the short distance, if you use club 1, we assume that you can have a 30 meters distance. And then if you use the number 2, you can have, you reach 10 meters, and number 3, 20 meters, and so on. Okay, so this is the table. And when you see this, you should already by now know that this means parameters, data. And also this guy is a parameter, right? So question number 1, imagine you want to maximize the total distance that you can reach, but you don't want to exceed 330 meters, because if you are here, right, and the hole is here, ideally you would like to reach as close as possible, but let's say you don't want to exceed, because maybe imagine that this is the field, right, and then imagine that here there is water. So you don't want to go above 330, because otherwise you have a penalty, you are in the water, and then you have a problem. Okay, so this is one condition. The other one is, actually there are 3 of them. Number one, we can use at least one club in the group S. So one for the short, one for the medium, and one for the long distance. Okay, so we need to use at least one of each. Number two, you cannot use more than one club for the short distance. In the first version of the material I put online, this was a 2. Actually, it's a mistake. So this is actually 1. Okay. If you have downloaded the previous version, there was a 2, but it's a 1. And you cannot hit more than 3 times. So any combination you choose, you are only allowed to have 3 shots. In golf, this is called sometimes par. So it means that you are supposed to hit the hole in 3, and whatever you do more than that, you have some kind of penalty. And if you do it in less, it's better. But let's say that you want to have maximum 3 shots. So the question is, can we formulate a binary linear programming problem in AMPL to find the clubs to use? And the question is, when you see the solution, can you reach the hole? Okay. Now, remember in the first lecture, I told you that at some point, especially when you have more complex problems, you may have a step where you have to interpret the solution and translate it back in the, let's say, domain of the original problem. So this could be a simple example to understand that. We have a problem, we want to know if we can reach the hole, and then we can solve this problem. And then we look at the solution, and then we are able to answer this. Can we reach that hole or not? Question number 2 is interesting. We can deactivate, this is something new that you have seen, but it's important because it will be in the homework as well. We can deactivate one of these 3 conditions, A, B, and C. So we can deactivate one of them. And we want to know which one we should deactivate in order to reach the hole. So imagine that here you cannot reach the hole. Well, now you know, because I'm telling you that you need to deactivate one constraint to do that. So which one should we deactivate to reach the hole? And then you may say, hey, very easy. I solved one problem where constraint A is not there, one problem where the constraint B is not there, and one problem with the constraint C is not there. And then I check. What is the difference here? I want you to determine that by solving a single problem. So this approach of I remove one by one is not feasible. We need to find the solution by solving one single problem. And I will show you how to do that later. Is it okay so far? So, as usual, let's start with the 4 elements of the problem that are parameters, variable, constraint, objective. We know that we cannot exceed the hole that is 330 meters away. We know the table that I showed you in the previous slide, where you have the distance you can reach with each club. We also know that we need to use at least one club for each type. So this was constraint A. Then we have the constraint B, that is we cannot use more than one club for the short distance. And then constraint C, we can only hit 3 times maximum. Okay. Next, objective, we want to maximize the total distance. So it's a maximization problem, and we also have the objective function that is total distance. What is the variable here? What do we want to know? Well, for each club and each type, we want to know if we use the club or not. So we go back here. For each element here, short number 1, short number 2, short number 3, right? For each one of them, medium 1 to 3, long 1 to 3. The question is, do we use it or not? 0, 1, right? We use it, yes, is 1. We don't use it, is no. So you see here, especially for Tanya, who was asking, this is an example of how we can use binary variables. In this case, we have a lot of yes, no decision to make, and therefore we can model that as binary variables. Okay, so we have the constraints here that I already mentioned. We can use each club once. That means is 0, 1. So if I tell you we can use each club no more than 3 times, it will be an integer, right? 0, 1, 2, 3. But in this case, because it's only once, then it's basically a binary. Yeah, basically, yes. Is that the only difference is on top of that, we have also some constraint, like we cannot exceed the distance, and then all these constraints you see here, basically. Okay. Actually, here the distance one is missing, I think. Yeah, these are the constraints ABC, what we call ABC, and there is also one missing, that is the max distance is 330 meters. Okay. So how can we model this problem? Let's start from the mod file. So we have the types of clubs, so short, medium, long. Then for each one, we have 3 of them, if you remember. We have a parameter max distance that is a 330 that is specified in the data file. Distance club is the table. Okay, so for each type, SML, short, medium, long, and for each club 1 to 3, we have the maximum distance we can reach with a shot. And then we have the variable that is for each club type, and so basically short 1, short 2, short 3, medium 1, 2, 3, long 1, 2, 3, a binary variable that is telling us, do we use it or not? So you see here the keyword binary. And again, this is the same as integer, where we specify greater than or equal to 0, less than or equal to 1. But because binary is very important, there is a specific keyword to represent that. Objective function is, again, the maximization of the sum of the distance. So this is the distance we reach times x. Why? Because if x is equal to 1 and we use the club, then we have to include the distance. If it's 0, we are not using the club, so we are not counting that in the sum. Okay. And then we have the constraint, so we cannot exceed the distance of 330, that is max distance. Basically, the total distance is the same as the objective function, if you see, is the same expression. Okay. Less than or equal to max distance. Constraint number 1, we have to use at least one small, one medium, and one long. So what does it mean? For each type, small, medium, and long, the sum in the clubs, so club 1, 2, 3, must be at least 1. So we must use at least 1 for each type. And then here we are saying that for the club short, we cannot use more than 1. So the sum here is less than or equal to 1. Now you probably realize that if we combine these two, for the short distance, we are basically saying that we can only use one short distance club, right? Because here we say we must use at least 1. Here, no more than 1. That means 1. But anyway, yeah, something that, yeah, maybe I can highlight. Remember, at some point I told you that there are different ways to model a problem, and sometimes it can be more efficient to solve. Now, if in this case, it will not make a big difference, but basically, if by looking at these, I know already that the short distance is equal to 1, it may say some variable, right? And actually some constraints, because instead of writing these and writing these for S, we can just write that the sum x of S in C is equal to 1. And this may simplify the resolution. Anyway, that's just a detail. The last constraint is no more than 3 shots. So we sum for all the variable x, that is basically saying if we use it or not. We cannot use more than 3. So what happens when we solve that? Well, first of all, of course, data file. So we have the max distance, and you see here the table. So here we are specifying a table, and the format is as follows. You write parameter, the name of the parameter, then you have these, then is followed by this. these 1, 2, 3 are basically the indices of the columns. These are the indices of the rows. And then you have these before starting to write the data. So this is more or less the format you use to define a table of data in AMPL, okay? So you see a little difference from here. The difference is basically that between the name and these, you have this expression, okay, that is basically telling you what are the column names. That's more or less the difference. And then, of course, we want to solve the problem. So we have the usual stuff, model is this, data is that. We want to use simplex and we want to display the solutions. So what happens when we solve this? Okay, first of all, optimal integer solution. So we are happy. Objective 320. So we are not happy. We didn't reach the whole because it was 330, but the maximum we could get is 320. And what is the solution? So you see, we are using the long distance club number 2. We are using the medium distance club number 3 and the short distance club number 1. Okay, so L2, M3, S1. L2, M3, S1. So let me write it. L2, M3, S1. So S1 is this, right? M3 is this, and L2 is this. If you sum, is 290, 320, the sum, right? 190, 130. This is the meaning of the solution, okay? Is it okay so far? Any questions? No? Okay. So let's move to the question number 2 that is interesting. How can we deactivate stuff? As I said, we cannot solve the problem by removing one by one the constraints. So how can we do that? First of all, we need to understand what deactivation means. So deactivation in theory means that we are not using the constraints. In practice, to do that, we can make the constraint always true. Because if the constraint is always true, then it's like not having the constraint, right? So how can we do that? As I said, we make sure that it's always true if we deactivate, and then we need to decide which one. Well, we just learned that to decide something, we can use binary variables, right? So let's see how we can do that. Let's start by the first condition. Remember, it was this. We must use at least one small, one medium, and one long. Now, this means that the sum, we have a sum of variable x greater than or equal to 1. But because we know that x is binary, okay, we also know that the sum of x is always greater than or equal to 0, right? Because it's a sum of 0, 1 variables. Worst case, it can be 0. It cannot be below. So how can we deactivate this constraint? Look at this. We write that the sum of these is greater than or equal to 1 minus y of 1. Let's say that y in 1, 3 are binary variables telling us if the constraint 1, 2, 3 are activated or deactivated. So y1 is a binary variable equal to 1 if the constraint A is deactivated and 0 otherwise. So see what happens here. If y1 is equal to 1, we are saying that this is greater or equal to 0. That is always true, right? And because it's always true, it means that this constraint is deactivated. Whatever the x values, this is always true. But if y is equal to 0, then this is equivalent to the previous one, right? It's the same thing. So basically, by introducing this new constraint, this new variable y, we are able to have a condition where if y is equal to 1, this constraint is deactivated. If y is equal to 0, we go back to the original one. Is it clear so far? Because this is very important. Yes?
So I imagine there are several ways to achieve the exact same concept. For example, you could multiply it with the variable y. Then if it's 1, then you keep the constraint. If it's 0, you deactivate the constraint. So what would be the difference in computational complexity, if any at all, if we take
yes, there are definitely many ways. In this case, I don't think you will see any difference. The difference will be sometimes if you have, let's say that this expression here, instead of 1, you have some other function of x or other variable z, whatever, right? So now if you need to multiply your y here, right, then you can have a difference. So what I mean is this. Let's say that this was greater than or equal to another variable z, okay? So then you say, hey, I could multiply these times, let's say y, we call it y of 1, right? So if, well, or 1 minus y actually. So if y is equal to 0 is the same. If y is equal to 1, I multiply by 0, so it's becoming 0, right? Or the other option could be is greater than or equal to z, and I could do something like minus, let's say a big number, y1. So if y is equal to 0, is the same. If y is equal to 1, I get that this is greater than or equal to a negative number that is always true. Okay, so what is the difference here? In this case, I'm multiplying two variables. So I need to linearize this with the technique that I mentioned earlier. Sometimes you need to linearize products. So we will not discuss this here, but it can happen. Or this is called the big M approach, where you are basically avoiding the multiplication. So it's better in a way. But on the other hand, if this number is very big, it can slow down the resolution time. So it really depends case by case. Okay. And how many of these products you have, how big is this? If you can derive a tight value for this big M. So there are many things to consider. In this particular example, it wouldn't make a difference in practice. But it's a good question because you will realize when you have more complicated expressions, the way you linearize, the way you represent this kind of deactivation as well, can really have a big impact on the way the problem is solved, and therefore the resolution time to achieve the optimal solution. Okay. What about number 2? Well, this is different because now we have less than or equal to 1. So again, we want to deactivate the constraint, and then we have a variable, binary variable y2 because it's the constraint number 2. So this was the original one, right? Now, what do we know about this sum? Well, we know that the is 3. It cannot be more than 3, right? Because for S, we have 1, 2, or 3. So what we can do is this. If y is equal to 0, we got the same as here. But if y is equal to 1, then we are saying that this sum is less than or equal to 3. That is always true. Okay? So it's the same principle, but it's just working on the other way because now we have a less than or equal to condition. And finally, similar here, we cannot hit more than 3 times. We know that the maximum value for this sum. So if you look, when you have a less than or equal to, you have to look at the maximum value. When you have a greater than or equal to, you want to look at the minimum value. Okay. And therefore, here you say if y3, that is the last binary variable, if this one is equal to 0, we go to the same condition as before. If this guy is equal to 1, we are saying that the sum of x is less than or equal to 9. That is always true, because remember the table, we have AMPL 1, 2, 3. We have 9 clubs, and each one can only be used one because it's a binary variable. So definitely the sum of x is less than or equal to 9. Then you may say, hey, but what if this 6 I put instead 200? Is still okay? Yes, it's still okay. It's still valid. The difference is less tight. So usually, let's put it this way. The tighter it is, the better it is in terms of finding the solution. Okay? But it's still valid. It's still valid. It's related to that big M thing that I mentioned before. So is it okay so far? How we deactivate constraints? You see, we are not actually removing one by one, but we are allowing the AMPL and Simplex to decide for us which one to remove. But of course, there is a missing point. We can only remove one. So how to do that? This is the formulation now. We have introduced these new binary variables, 1, 2, 3. This is what we have discussed. And to say that only one can be removed, this is the constraint we use. The sum of y is equal to 1. Only one can be 1. Okay? Is it okay so far? If something is not clear, just stop me. Yes. Wait. Okay. So what is the solution? Well, the data is the same, the run is the same, and then we get this. We basically see that we have deactivated the first one. This was constraint A. You see that we are using one long and two medium. Remember, the constraint A forces us to use at least one short, one medium, and one long. Now we are not using short anymore, but now the good news is we can reach 330. Okay? So maybe in practice, if you really play golf, it doesn't make sense, because when you're getting close to the hole, you want to use like some kind of clubs that are more precise and less distance. So don't take it as oh, we should play golf like that. No, but we are assuming here that we are really good, and then whatever the distance is what we can get with a shot. Let's see the discussion of the solution. So we have deactivated the constraint A. This is the optimal solution. So it's 180 plus 150, that is 330. We can reach that hole. Great. And again, it's possible maybe that there are symmetric solutions. So maybe because this is Simplex, right? It just show us one solution. Maybe it was possible that by deactivating this one, right, or maybe this one, we can still find the solution. Who knows? It's possible. But at this stage, we don't care. We just wanted to see if we could get the solution. So what you can do if you want to check alternative solutions, you may, for example, say, hey, I know that I can find a solution where the first constraint is deactivated. What I can do is I can force y of 1 to be 0 in the model, and then see if I can reach 330 with this or that. Okay, this is a possibility. And I also wanted, before moving to the session that we can start after the break, I wanted to show you, to discuss something. Let me go back here. Okay, so imagine that we have only two. Okay, imagine that this is not there, just for the discussion, okay? Because you may find problems like that. Imagine that this is not here. We only have two conditions. Do we really need two variables? Because here we have y1 and y2, right? This is in 0, 1. This is in 0, 1. But then we know that the sum is equal to 1. So y1 plus y2 is equal to 1. Therefore, we don't need y1 and y2. We just need a single y. So let's say that this is y. And this one, we can call it 1 minus y, right? Because of this relationship. So you see, this is another example. In this case, by looking at the problem, you are able to save one variable. Because now you don't need y1, y2, you just need y. And the relationship between the two can be written like that. So this works because we have, and also you don't need that anymore. This works in case you have only two. But imagine that you have a couple of variables for, like is indexed by another set. So you have y, 1, 2, and then you have another set k with a lot of elements, maybe 1 million elements. Then you're basically cutting in half. Instead of 2 million variables, you have 1 million variables. So this is just to explain to you that working on the formulation sometimes can have a big impact in terms of resolution time. And you will not see that in problems like that, but when you find more complicated stuff, spending some time to try to make the formulation more compact can be beneficial. Okay. So what I will do now is 3:50. First of all, do you have any questions before we move to the break, basically? No? Okay, so what I will do now is we can have 15 minutes break. So we come back at 4:05, and then we go with your session, where you have, I will divide you in breakout rooms, and then I will show you the last homework. Okay? So see you in 15 minutes. Okay, is everyone back? Yes. Well, of course, if someone is not back, he will not answer, but I think we can move to the next part where I will show you 3 problems that are based on what you have seen before on the golf problem we solved together. So what is your task now? Problem number 1, you need to find a solution of this problem where you want to minimize the number of clubs to use in order to reach the hole, where the constraint A applies. Okay, so constraint B and C, no, and you cannot use more than 1 club for the short distance. Okay. So this is one. The second one is like the number 1, but also there is another constraint that you must use 1 club for the medium distance. Okay. And then the last one is basically you remove all the previous restrictions, okay? All of them. And you can use the 9 clubs as many times as you want. So let's say that you have a short distance number 1, you can use it. Wait, there is a question. Okay, isn't you cannot use more than 1 club for short distance. Oh, yeah. Basically, the problem is that in the previous version, as I said, there was a a typo. So in the first version, that was a 2, right? So that's why you see this inconsistent value, because yeah, there was basically a typo that I correct, but then you see this and it seems like a new condition, but it's because the previous version there was a 2. And I was saying this one, make sure that the previous restrictions, they do not apply anymore. Okay. You just want to maximize the distance. So even like constraint A, B, and C, and the maximum 330, and also the fact that you can use each club once, all of them, they don't apply anymore. Okay.
It wouldn't just, there would be no defined solution, right? You can just use them an infinite amount of times.
Well, you will see, like, one of the things is really to see what is the output of Cplex in these cases, and then we will comment that.
Okay.
So I will split you in the breakout rooms. Let me do it right now. So we are, I think I can have 3 rooms probably. Okay. And by the way, I think now it's 4:10. We can come back at 4, I don't know, 30, like I would say 20 to 30 minutes. Then I will check the rooms, and if I see that everyone is done, we can come back earlier. Okay. Okay, so let's go to the solution of the problem. And we start with the first one. So here we want to minimize the number of clubs to use in order to reach the hole. And we have constraint A still valid, but B and C are not there anymore. And then we cannot use more than 1 club for the short distance. That was basically like the B, but I explained there was a change in the description. So what happens here? Well, what you see here is that now we are minimizing this, the sum of the variable X that represent the number of shots. So we have that constraint. What happens when we solve the problem? We basically get this objective 4, right? Did you get the same?
We got
Hello?
3. We got 3, I think.
We got 4.
3 or 4
as well.
Okay. So maybe later we can check why you got 3.
Yeah.
Because this was not the most interesting. To me, the most interesting is the 2 and 3, the next 2. But we can discuss later about your solution if we have time, because I want to keep some time for explaining how to say, for explaining the homework. But are you sure you keep constraint A? Because if you get a better solution, maybe you remove some constraint.
I think we got it, but let me check later. Yeah, that's okay.
Okay, we can do later. Okay, what about number 2? This time you must use exactly 1 club for medium distance. So basically you have this condition over here, right? You can use 1. And what happens in this case, you solve the problem and then you get this condition here, integer infeasible. Did you get the same?
Yeah.
Yeah. So what does it mean infeasible problem? It basically means that the feasible region is empty. It's like, I give you an example. If I ask you minimize x subject to x greater than or equal to 0 and x less than or equal to -5, can you solve this problem? No, because if this is the domain and this is sorry, like -5, right? You're saying that you must be here, but you must also be here, and there is no intersection between this and this. So basically, it's impossible that you find a solution where both of these are respected. So when you find an infeasible problem, it means that it's not possible to find a solution that respects all constraints. Now, what you see here is telling you that there is a value for the variables and an objective function. If the problem is infeasible, it doesn't mean that this is a valid solution. Usually it's the default values. So you cannot say, hey, the solution is to have 0 everywhere and this is 0. No, this 0 don't mean anything when you see that the problem is infeasible. Okay? So, as I say, there is no solution respecting all constraints. What you see is not valid. And what happens if this is the case in a problem you are solving in your research, for example? What you need to check is that all constraints are correct. And also, if the problem is infeasible, maybe it means that your assumptions are too strict. Maybe the way you are modeled the problem is making it impossible to be solved. So you need to, assuming that the constraints are correctly stated, you need to relax something about your problem. Okay, because the way you model that, you cannot find a solution. Any questions about infeasible problems? No? Okay, so we can move to problem 3. Now, in this one, you can use the 9 clubs as many times as you want. And also all the previous restrictions, they don't apply anymore. And we want to maximize the distance. So you may already kind of expect what happens here. But basically, when we solve the problem, we want to maximize the distance, that is this, right? So for each club, if we use the club times the distance, but this time is not binary anymore, because we cannot use the club only once. We can use the club as many times as we want. So what is the solution when you solve this? Unbounded. So unbounded means basically that for every solution you find, there is always something better, right? So it's like to say, hey, maximize x subject to x greater than or equal to 0. What is the optimal solution? Is infinite, right? Because every solution you find, there is always something better. So basically, this is called unbounded problem. And again, when you see the solution here, all these values, the 0 and 0, they are not a solution. It's like before, only default values. When you see unbounded or infeasible, you cannot take the solution that is displayed and say, hey, this is the optimal solution. No, it's just a problem for which a solution does not exist. In the infeasible and unbounded, there are an infinite number of, as I explained, every time you have a solution, you have something better. And so therefore, there is no solution in that sense. So again, unbounded problem, as I say, you can always find a better solution. What happens is that the solution displayed is not valid. And if this happens in reality, usually is the opposite. So when you have an infeasible problem, it means probably that you have too many constraints, so it's too tight. For unbounded, usually is when either you forgot some of the constraints, or maybe again there is some error in the way you wrote them. Infeasible problem, I think, is possible. Unbounded problem, in reality, I think they are quite unlikely. So if you find an unbounded problem, mostly the reason is that you forgot some constraint, or you wrote the constraint in such a way that is maybe some of the parameters are wrong. You use a wrong number or something like that. A wrong sign as well can be. Okay. So this is more or less the solution of this activity. And the reason why I wanted to show you this is because now you have the full spectrum of possible outcome when you solve an optimization problem. That means you can have a solution, you can have no solution because infeasible, or no solutions because it's unbounded. Any questions before we move to the homework? Okay, so last 10 minutes, let's discuss about the homework. Similarly to the other time, you need to submit the mod run file. Again, data file is not required here. This is the format, but I will upload the instruction. Is more or less like last time. This is the deadline. Okay, so is this Friday at midnight, basically. And same thing about the score. Okay, so this is the problem. So if some of you are familiar, I know, for example, Andrea may know that there is a kind of magazine in Italy, it's called Settimana Enigmistica. Is like a lot of games like the crosswords and things like that. And then they had some games sometimes that are like, how to say, some challenges that this is more or less one of them. And of course, they would like you to solve it by thinking, but I thought that this was a really, really good example for integer linear programming. So what is the problem? Let's say there is this guy, Mr. Alvaro. He goes to the Luna Park with the nephew, and the kid is having fun and blah, blah, blah. And then the guy is looking at a technician that is switching some lights with some carousel, right? And then the technician is explaining how that works. So there are 5 programs, okay, and they can be run together to basically command these lights. And the way they work is this. So the program number 1, when this program is activated, is saying that the red lights are on when the yellow lights are on. So in other words, if red lights are on, then yellow lights are on. So this is an if-then condition. Program number 2 say that the red and the green cannot be activated at the same time. So they cannot be together switch on. Number 3 say that the blue and green, they are either on or off together. So either they are switch on together or switch off together. The number 4 is blue and violet cannot be switched off at the same time. And number 5, if the violet lights are on, then the blue and yellows must be on as well. So if you see, basically we have a few lights, blue, violet, green, red, and yellow, that can be on or off. And then we have 5 programs, so 5 conditions that can control that. So your job is to answer to these 2 questions. Number 1, formulate a binary programming model to determine which lights are on when all programs are activated. Okay. In other words, if all these 5 conditions are working, what are the lights that are activated? The second question, that is a little more challenging, you can deactivate one of these 5 programs, one of them, only one. And you want to formulate a single optimization problem to determine the program to be deactivated for achieving what? You want that as many lights as possible are on. So again, you need to find the program that should be deactivated so that when the other 4 are running, you have the maximum number of lights that are switched on. And to do that, you need to formulate that as a single optimization problem. So as we have seen before, we cannot remove one by one the condition and see which one is like which problem give us the solution we want, but you need to use some binary variables maybe to determine the condition that is deactivated. So a few hints as usual. Question number one, if you realize here, I didn't specify anywhere an objective function. What is the objective here? There is no objective, right? We just want to see which lights are on when all these 5 conditions are used. So in other words, I tell you that there is only one feasible solution. And if you have only one feasible solution, the objective function doesn't matter. Okay? So this is the hint. If there is no objective function in this case, it's not a problem because any objective function will give you the same solution. Why? Because there is only one solution. For question number 2, you need to deactivate one of the 5 programs, right? Only one. And you have seen in this presentation how to do that. So what you have to do, you have to think about how to use binary variables so that each condition is either the original one or always true. Okay? So this is the homework. I will upload on the website the assignment and the slides. This is the deadline. After the deadline, I will take some time to revise your submissions together with the submission of the first homework, and then I will upload the ranking. Okay. And then, as I said, for those who participated and are in the first, I will see how many positions, I don't know yet. There will be some small gift, maybe some voucher, still in discussion with the management. But that's why I suggest you to submit, not just for that, also because I think it's by practicing that you will learn and understand better what we have done. So that's the end of the course. Thank you a lot for being here, for participating. I hope you find it useful. I hope you have a better understanding of the basics of optimization, what you can do with linear programming, integer and binary programming, how you can model problems with AMPL, the kind of process that you need to follow when you move from the description of a problem to a model, to a mathematical programming, let's say, model, yes, that you describe with a language like AMPL, how you solve it with solver like Cplex, and how you interpret the solution, even when you don't get a solution because the problem is unbounded or infeasible. So that's all. If you have any last questions, feel free to let me know. We still have a few minutes. Otherwise, I would say that, first of all, good luck for the homework, especially number 2 may be a little challenging, but I think it's a good exercise. If you have questions even after the end, you can still write to me and I will do the best I can to answer. I will upload this last lecture, the video and the slides, as soon as possible, probably later today. And that's all. So thank you again for participating. And as I said, if you have any last questions. No? Okay. I may also send at some point maybe a survey just to get some feedback to understand what you like about this course, what you think can be improved, and so on. So if you receive that, please fill it, because it will be very important for me also to get a feedback, and therefore if there are other courses to prepare, also make something that is closer to what you expect. Okay. Oh my God, no convex optimization, not that. I refuse to do. If you want non-linear, if you want black box, but convex, I should not say, but I hate that. Okay. Thank you guys. And well, again, do your best for the homework.